My name's John Ogbu. I go by Ike, and I'm studying electrical engineering. My thesis project is titled Voltage Regulator Module Design using wide bandgap semiconductors for graphics processing units. And so the idea of the project is to use wide bandgap semiconductor-based devices, namely silicon carbide and gallium nitride, in order to improve power efficiency in power conversion for graphics processing units in data centers, like the ones that you see that power Claude, Gemini, and ChatGPT. Data centers, especially these hyperscale data centers that power these large language models, use a ton of energy. So we're talking in the order of hundreds of terawatt hours. And so when you're dealing with that amount of energy, every single percentage point matters in terms of power efficiency. And so the solution is to make every step of or ideally every step of the power conversion from the grid to the actual GPUs that are performing the computation as efficient as possible. My project focuses on the last step, which is from the servers within the data center to the GPU, which is typically on the order of 12 to 48 volts to about 1 volt. And so this kind of paradigm that we've been using for the last decade or so uses silicon transistors because they're the dominant device type, or dominant transistor type. However, as large language models, their compute needs continue to increase, they need more power. The GPUs need more power. And so as GPU power requirements increase, the current draw also increases, which increases losses ultimately. And also makes it more difficult for certain devices, certain silicon devices, to handle that level of current. And so I was looking at wide bandgap semiconductors as an alternative because of their lower on resistance, or, well, that is device dependent, but potentially lower on resistance, thus lower loss at this in this regime, as well as their better switching characteristics, as well, minimizing switching losses, the same vein, yeah. So this project was quite interesting because this was my first power electronics experience whatsoever. I didn't know anything really about power conversion when I jumped into this project, so it was a huge learning experience, but I really enjoyed it, like from the theory and understanding, like on a device level and on a material level, right, the different properties of these materials, then how that emerges on the device level, right, and what choices you're able to make to design these devices, and then how does that affect like the circuit and eventually the system level performance. That kind of full stack analysis was super interesting. The actual build process as well had its like ups and downs, but I learned a lot, definitely. So I'm going to be pursuing a PhD at UT Austin in electrical engineering, and currently my plan is to do something in intersection between power conversion and materials, some magnetic materials or so, at least initially. We'll see what the future holds though.